I guess I'll see if my voice and upper respiratory tract seem to cooperate this time. Um, yeah. So it's been a little while since I did any streaming um, or status updates on my project. Figure I'll talk about it some. So development has continued and working on various stuff. Not quite mature yet, but gradually getting there. Bus is now implemented, and virtual memory is more or less working. Not entirely stable yet, but for the most part, well, the actual MMU part works. The actual um, mapping stuff to the page file and stuff like that is still a bit more experimental. But yeah. So recent features are I've added dual ISA support for RISC-V and another extension called XMOV, which can extend the virtual address space to 96 bits. I'll get to that later as well. So yeah, for the RISC mode, so it works basically via an alternate sub mode and a separate decoder, which decodes RISC instructions. It aims to map it to the existing pipeline, so it's not really like a entirely separate implementation or anything, but straight up more of a decoder hack. The pipeline for RISC is close enough to that for BJX2 that it was more or less I was more or less able to make it work, sort of. It's still pretty experimental, not really well tested yet. But sort of in theory kind of exists. For now I'm focusing on user mode, not really on OS level features. Partial reason is well, the way the stuff, a lot of the hardware works and other stuff like that is enough different from RISC-V to where doing an OS kernel entirely in RISC-V is not yet viable. Could be done in theory, but would be a bit more work and probably require some redesigns and other stuff like that. Yeah. For now, I'm primarily focusing on the RV64i subset, so it's pretty minimal. Basically, more or less. Yes, not sure that not off or not. I see my still life. So yeah. But so for now, yeah, primarily it's an integer subset of the ISA. May support the ZFinX extension sort, so FPU via GPRs, because yeah, my current FPU does via the GPRs rather than having some register file. Much beyond like this subset of features, things don't line up particularly well RISC-V and BJX2. So yeah. We'll support an ELF loader as noted. The existing compilers like GCC and similar primarily produce ELF output for this target, so that's what I'd probably be using in this case. Okay. Still live. Here to still be live. So, yeah. But yeah, so yeah. So I'll have yeah, an ELF loader for this target. This will be used in parallel with with the L loader that I'm using for BJX2. So yeah. The state for which mode it's running is like stored in the instance status register flags, and it's possible to fairly readily switch between modes via jump or per thread. So so both instruction sets can more or less exist in parallel at the same time on the BJX2 core. But yeah, the limitation is it lacks the M, A, F, and B extension. So this would basically be multiply and divide instructions, which don't map over exactly because my multiplier is different and can't implement instructions exactly the same. And also there's no divide instruction. Atomics are well, there's no direct or no direct analog of the RISC-V atomics in BJX2. There's volatile load and store cases, but they're currently a bit different from the atomics. F and D don't map mostly because of the use of a single register file. It would be possible in theory to map the floating point registers to R32 to R63 or so, but the way RISC-V is designed, I can't really do that at the same time as the Z Phoenix. So yeah, it's a trade-off. It could be one or the other. Doing the F or D extensions crappy, or doing Z Phoenix or having it slightly less crappy. So yeah. These extensions don't really map well to the existing pipeline. So yeah, BJX2 only provides 32-bit integer multiply option, no integer divide. Partly that's for both latency and cost reasons. Namely, it's a lot easier to make a 32-bit integer integer multiply semi-fast and make a 64-bit integer multiply semi-fast. And integer divide is, well, it's not super common, or it's not a super common operation, and also fairly expensive to do in hardware, so I'd mostly just left it up to software to sort that out. You can basically implement both larger integer multiply and integer divide in software. So it makes incentive to provide hardware instructions for them more so if they're expensive. A bit lesser. So yeah, the floating point unit uses GPRs and does not provide divide or square root. So likewise, this is similar to the integer case, namely you can provide them, but making them both fast and cheap in hardware is not so easy. I'd at one point or much earlier in the development, I had these operations in hardware, but they were not super cheap, and they were pretty slow. And I was actually able to do faster floating point divide and square root actually in software than my first hardware. So yeah. So it's basically it's basically analogous to C Linux in terms of what it does, but not so close to FD extensions. There's no microcode in the BJX2 core, so no real good way to emulate missing instructions. And emulating them via traps or interrupt handlers would be really inefficient. So I'm not really that inclined to go that route either. However, yeah, the trade-off is that most of the existing binaries assume the RV64 PC ISA like variation. So yeah, this would basically be most of the RISC-V Linux ports and other stuff like that. Which is, yeah, for now it's kind of a problem. And these things can't really be added cheaply. And yeah, that's kind of a problem. Like, you try to add a feature and it blows out the resource budget on the FPGA. Well, that's not really going to work. Yeah, and if they were cheap, I would have done them already. So yeah, lots of corner cutting. Yeah, the viability of pure RISC-V binaries is debatable some. I could in premise do like pure RISC-V binaries, but the instruction set does have some design limitations that make it, or would make it less efficient in terms of its performance and other stuff like that. And some things would be better handled by having parts of the runtime switch over to the BJX2 ISA to use that for things that need to be faster. Yeah, RISC-V works, at least in theory. So but with the limitation that it would have to be pretty much straight RV60 or I for now, which is fairly limited subset. Possible to jump between instruction sets on. So yeah, if you jump to an address with the least significant bit set, it will jump between instruction sets. On in RISC-V mode, this does slightly violate the specified behavior for the or the how to say this instruction JLR or similar or something. But yeah, but it does slightly break the specified behavior. But from what I can tell, binaries generated by GCC or similar should be able to survive this slight infraction. In particular, the spec says that the least significant bit is ignored, whereas in my case it's not ignored. It just needs to be come out as zeros for jumps within RISC-V code. For the link register, the high order bits also encode the mode. This allows basically for inter-ISA function returns. So if you call a function from RISC-V mode to BJX2 mode, then you can do whatever in BJX2 code and then return back to RISC-V. However, the C APIs are different. So code would need to either be aware of the API differences or use thunking. For runtime support functions that are intended to be called from RISC-V mode, the thunking could probably be avoided, since then they would just be using a hacked version of RISC-V API on top of BJX2, and it can at least work in this direction. The other direction wouldn't work out quite so well because there are registers that exist in BJX2 that would be inaccessible from RISC-V mode, and there are also a few registers that exist in RISC-V mode that would be mapped to control registers in BJX2 mode, so it's not quite one-to-one, but yeah, good. The parts about cross-ISA linking and thunking similar is still on the to-do list for now. Oh yeah, but yeah, should be able to work similar. So yeah, so it's theoretically possible that I could cross-link ELF from the ELF binaries to the PEL binaries. Say the ELF or RISC ELF binaries, the main binary, versus the PEL binaries would be taking the role of the shared objects. So for example, the C library similar could potentially be BJX2 code, whereas the main program could be ELF code, or could be RISC-V code in the form of an ELF binary. In this case, yeah, the program loader would need to handle any of the thunking and other things. So yeah, but one downside, while GCC is pretty clever, mostly in the context of optimizing things and so on. The RISC-V ISA isn't super great in some areas. Yeah, pretty good optimizer, but would not be particularly efficient. So it would be able to do one cycle per instruction for most cases. However, due to some design limitations, RISC-V would need to execute a lot more instructions to do similar tasks. So, yeah, BJX2 is more optimized to do more work per cycle, namely fewer instructions to do similar operations, and also the way that it can be executed can be packed more densely. Unless, of course, it so happens that like RISC-V can run quite effectively at 50 megahertz, but not really tested that. Would be a little bit surprised if it worked effectively, short of like, short of GCC pulling off a kind of optimizer miracle or something. Yeah. So yeah. So yeah. On to addressing now, it looks like. So yeah. So BJX2 uses well 48-bit base address. So low 48 bits is used as a base address, and the high bits are used as a tag value. They're mostly ignored by the CPU. So, for example, load and store instructions will generally allow the high 16 bits to contain whatever. These are used as tag bits by the C runtime, for example. Yeah, the variant type system, which does dynamic types, that basically uses the high 16 bits as tag bits. And for object tagging and other stuff like that. This whole setup has been a subject of a fair bit of debate, but it generally works and should be sufficient for most things. However, yeah, I have kind of engineered myself into a corner here. And yeah, some could argue that 64-bit flat addressing would be better, like that used on x86, 64 or ARM and similar. But yeah, this ship is already sailed. Code, or a lot of the existing code, kind of assumes that it works this way, and suddenly switching out to a purely flat addressing scheme would probably break a lot of existing stuff, like primarily in my runtime libraries and other stuff like that. Namely, if I wanted to, still keep using a similar tagging scheme, I'd actually have to mask off the pointers and stuff, or yeah, mask off the addresses for accessing memory through them, which, well, yeah, that's an issue. And some amount of code is written with the assumption that it can access memory through a pointer without having to mask off the low bits first. So for the normal C pointers, it doesn't actually really make any difference because most of them are using the 0 or just a straight 0 tag. So Um, so yeah, it's like the pointer's already been passed off, but for dynamic object types, like in BJ, or like in my BJX script languages, and so on. Yeah, then this would be an issue. So X, yeah, XMOV extends the address space to like 96 bits via quadrant addressing scheme. Yeah, in this sense, it's sort of like a supersized 8086. Or I can't really fit it in the text here, but it's also sort of like the 65C816 in that sense as well. But so it's, yeah, in some ways closer to the 658 or 65816 than it is the 8086. Um, yeah, hmm, that's its own thing. Hmm. So there's a PCH for the high register for PC. This is basically says the hmm, where the code is at, and then the GBH is basically the GBR high register, which says where the data is at. Yeah, these would basically be analogous to the code segment, data segment registers in the 8086, or the PB and DB registers in 65816. So, yeah, so these put a 48-bit quadrant somewhere within the larger 96-bit space. So it just sort of tags the two halves together. So we'll take the high order bits from one of these two registers and glue it onto the low 48 bits from the base register. So you'd use PCH with the low 48 bits for branches, or GBH and the low 48 bits for loads and store operations. Get into this a little more later. There's also VBH and SPH. Does SPH still exist? I think I might move that one. But yeah, yeah, that's a little better. So yeah, there's a high register for the BBR, which is, you know, used when interrupts occur, and also a high register for safe PC, so that well, so that we can actually get back to the code, the ISR. Things like setting up the stack or setting up the stack into the correct part of the address space will be left up to the interrupt handler. Um, but yeah, or use 96-bit addressing directly to access the stack, which is also theoretically possible. Yeah. Yeah, so there's also XMOV load store ops. These basically use a direct 128-bit add or 128-bit pointer with a 96-bit address field. These are basically register pairs, and yeah, can access the entire 96-bit address base directly. These currently use the var huge modifiers in C, and by default by default pointers will use the 48-bit addressing scheme local to a given quadrant as defined before. So yeah, generally ended up using the term quadrant rather than segment, but similar enough in concept, but I have my own reasons for using a different term. Well, partly the difference is segments in x86, like when you got to 386 and similar, or 286 and 386, went in a completely different direction than how I'm going with quadrants. So, as noted, in terms of function, they're actually technically closer to um, how it worked on some of the 65816 variants than it is to the x86. So, yeah. I've also defined defined something I'm calling a quad as the new base unit for dealing with large sizes. So here it's defined as roughly 2 to the 48 bits or bytes, or 256 terabytes. So 16 exabytes in the traditional scheme would be referred to as 64 kiloquads in this scheme. Likewise, the entire 96 address space would represent a unit of 256 teraquad. Yeah, partly this is because dealing with sizes this large starts to become kind of a hassle with SI prefixes, namely you kind of run out. Because the SI prefix scheme, it goes up to zeta and yada, but it doesn't go past zeta or yada. So once you can no longer express the size, in a single prefix like zeta or yada, then it becomes a lot less convenient. So if you offset the whole like base unit space so that say something like 256 terabytes or petabyte or whatever is used, then the prefix scheme goes a lot further. Technically, arguably, one could be using using the power of 2 like binary prefixes rather than sitting around using the base 10 prefixes, but this is more sort of a case of whatever. Pretty much everyone uses the traditional base 10 prefixes, like rather than like EV byte or MEV byte or whatever. That's kind of funky. But yeah. So either way, it's a workaround for the lack of prefixes. Um, oh yeah. So yeah, the TLB is also extended to support the 96-bit virtual addresses. Um, the physical address space is assumed to be a bit smaller for now. Namely, um, it uses 96-bit virtual addresses, but a lot of the design is still assuming the use of a 48-bit physical address space as well. While going beyond 48 bits for physical addresses right now is arguably kind of pointless. Like, even if one mapped all of the RAM and hard drive space and all that stuff in a typical desktop computer into a single address space, well, you still wouldn't use up a 48-bit address space. So it's kind of pointless to go bigger than that for something on an FPGA. But for there is at least non-zero. There is at least non-zero use cases for like 96-bit virtual addresses. So, and yeah, also I implemented them, and it turns out they weren't practically expensive. So that's kind of why I started going with this. Otherwise, I would have just been all like, whatever, and put it in a corner somewhere to leave for later, like some future time. But somehow the FPGA survived, so I'm going with it now. The bathroom break here. Okay, so I'm back. So yeah, the TLB is for 96-bit virtual addresses. And they're encoded in pairs. So, for example, the first TLB entry would be loaded as the high half, followed by the low half. The bit patterns within the TLB entries do encode which half of the TLB they're supposed to be in, or which half of the address they represent. So when you upload the high half, it sees from the bit pattern that you're uploading and then make special provision. And when the low half is up, is loaded, then it will load both the entries into the TLB at the same time as a conjoined entry. This is done partly for technical reasons. Individual programs still mostly seem to fit within 48 bits. So yeah. For now, like the 96-bit addressing is intended for things like the OS to use, or for particularly large programs, namely programs that need more than 256 terabytes of virtual address space. It's debatable how many there could be. Also, technically, the user portion of the 48-bit space is only 128 terabytes. So yeah, subtleties. Either way, for most programs, probably like 128 terabyte should be more than enough for anyone. Much like in the same like sense, 256 kilo quad. Actually, 256 tera quad should be more than enough for anyone. So yeah. Yeah. Not sure if anyone's picked up on the obvious Star Trek reference in a lot of this, but yeah. Super creative like that. But yeah, most programs don't really need to care whether or not XMOV exists, because from the point of view of the user ISA, if they're just using 48-bit addresses, everything is basically the same as it was before. They have a few more registers that they don't use, or they don't actually mess with, and the OS can basically, yeah, it shows for the program. But the bigger address space will be available if programs need it. And there's going to be there's actually a flag bit to say whether or not programs are allowed to use the bigger address space, partly, but that's more because you might want to be able to run a program in a sandbox mode. Use sandbox program within a given 48-bit quadrant, then like well, then it can't access anything outside of that quadrant if you don't allow it to. But but you can have the option to give programs the ability to access the entire address space as an alternative to having an OS with multiple address spaces, which you can also technically do on BJX2 as well, but it's all design trade-offs. Things like the variant type tagging system work as before as well, mostly because the base pointers are still 48 bits, so nothing changes as far as the tag bits are concerned, and the way the larger 128-bit pointers are encoded, it still leaves the same range of bits available for tagging in both halves of the register, or of the register pair. So instead of having 16 tag bits in a 128-bit register, you actually have 32-bit or 32 tag bits, just split in half as well. These could they could in theory be used for something as well, but probably that depends on things like ABI and other stuff. Oh yeah. Yeah, for the current tag system uses uses MSB tagging. So the high 4 bits they'll give the high 4 bits will give the major type for the reference. So 0, for example, is used for pointers to memory objects. With another 12 bits left for the object type tag, and the low 48 bits for the actual address. If it's 0, then it basically means it's an untagged pointer, like, for example, what you'd get from CMalloc or similar. For the most part, normal C code will just use tag 0 for most of its pointers. But non-zero tags are used internally, and for any dynamically tagged objects, then there will be type tags. So, this would basically be things like tagged arrays, and bounce check arrays, and similar. So tags 1 through 3 are used for tag 1 is used for like small value spaces, whereas tag 2 is now used for basically bound checks. Bound check arrays, which are limited to a relatively small bound check that they can bounce check. And unlike some other cases, the bounce check arrays don't actually need an object header. It's more sort of an optional feature, like if you want to be able to cast it to variant or similar. But otherwise, it's possible to just have a stack pointer with a bounce check on it for a small array, and then to encode it as a bounce check operation. So yeah. There will be a 62-bit fixed num type, which is there's a 62-bit fixed num type treated as a 2's complement integer. So nothing too amazing about this. This uses the high 2 bits as a tag rather than high 4 bits. That's why it has a range. Similar for flow num. Flow num is basically a double precision floating point value just shifted right by 2 bits. This is chosen over some other options like NAND tagging or similar. One could have argued for using the least significant bits as a tag and then not having to have shift double right, but um, solve trade-offs. Similarly, uh, overall, this works out faster than some of my past schemes, which tried to um, organize all the tag bits around like the encoding double, and using the shift representation or the out of range or high or large range values, which is a bit more hacky and slower. So for this, I just went with the option of shifting everything right by 2 bits. Some of the some like other values like C, D, and E are used for other things, but I just left them out here because not a whole lot of space. And then like it's possible that the F space can be used for larger 60-bit flat addresses. I have experimented with this already, namely by having the I address bits be added or basically added together to the bits from BJX2 to make it work like a translated like a translated 64-bit space or 60-bit space in this case, but it's not super great in terms of like resource cost or timing, so it's not great. High bits would be added to low bits of the quadrant to work on the translated space. This is still on a bit more of an on-the-fence feature. Not sure if it's actually useful enough to be worthwhile. So, because by the time you need more than the existing 48-bit limit, you can probably afford to use 128-bit pointers. So yeah. Not sure if there's much more I need to say right now. Yeah, basically what oh yeah, but also I had some experimental instructions for accelerating the handling of variant tagged objects as well. So objects basic or instructions basically to check either the top bits against the value or to check the low bits against the value, and also some instructions to do array bound comparisons and similar as well. These can reduce the number of instructions needed to encode a bound stretch array and potentially skip the need for using a function call as a handler. That's more speculative at the moment, or at least skipping over the use of a function call is more speculative, but it's at least in theory it could be done. However, it's a trade-off because as noted, balanced check arrays aren't used in C. They're more used in languages like Java and C# and similar, which can be represented semi-efficiently with the new instructions. But yeah, but C just uses raw pointers for everything, so it doesn't really need it. Um, and as noted, it's kind of simpler from the design perspective to have pointers which are effectively tagged by default rather than having to have a separate system for untagged pointers and for tagged pointer objects. As for why you'd want to stick like a type tag or bounds check in the pointer itself, that's mostly because the main alternative is that you have to access memory to get the type of, or to get the object type or the rate bounds. Extra memory accesses don't come for free, so it's easier to find. Um, so yeah. So here we can have an instruction that compares type in this format. This would basically checks 63 to 62. But, yeah. And say we have then we have another instruction like this, which basically if we have a type tag 2, then it will compare the bounds. So be all like basically be like that. So comparing the high yeah, the high order 12 bits which are used for the attribute or yeah, type attribute or R9 to use as a bounds check, and we can be all okay. So if either of these checks fail, then it will basically slow path and then like so um, so yeah, if it fails we go to the slow path, or if it's if the tag matches and if it's in range, then we just load it correctly. But slow path would basically be like argument registers. So in this case, like if it has to go to the slow path, it will load the two registers into the argument registers and call the load index handler for arrays, and then store the result in the destination register, and then basically branch back to where it completed the load. In this case, yeah, in the fast case, like tag matches and it's in bounds, this will add the latency of about 3 clock cycles onto the array load operation, which is a lot less than if you just always go down and do this. You have 3 cycles to do the register moves, and then however many cycles you spend on the and or function. So yeah, and that's one incentive for like for using dynamic or here's the encoding scheme for type tags. So yeah, it's basically compares a variable number of bits from either the high end of the register or the low end of the register. Yeah, and like parts of the media, it's using a 6-bit media. So this is a new addition, but technically it's using the RM and few bits from yeah few bits from the E field to get a 6-bit media, which is what it's using. And it's or it's using or your unary coding for like the actual length of the bit pattern to be checked. However, that works out pretty well in this case because, well, shorter value means longer unary code and they work out equivalently. If you were to store a 2-bit count, the 6-bit immediate field would have no longer been sufficient for being able to compare 4 bits of both the high and low position. So it works out probably reasonably okay. These instructions, which related to XMOV, these have existed a little longer, but they're useful for dynamic typing, and these ones can be used for either these can be used for either like array bounds checking or for type tag checking. So I tried to come up with instructions that would be reasonably generic, as in can be used for arrays or for other related operations, as opposed to something that's only useful for one thing, which is less desirable. And these instructions are do save a fair bit compared with what you have to write out if you are doing it with shifting and masking. So, yeah, so it could at least be useful in the fairly narrow use case, namely if you have a language. So yeah, if you have a language that does like arrays in this style, you create an array and an array of it opaque integer array type, and then you make a new array with a given size and so on, and then I is initialized exists, and this initializes something that's indexed. But if we do this here, then we can put it like up here and have it be not super awful and slow. Similar for dynamic typing, since since in dynamically typed code, like the dynamic types end up being used quite a bit. Namely, pretty much every operation that you do in a dynamically typed language also needs to be dynamically type checked. Well, then having instructions to help with these cases quickly or can quickly pay off. So yeah. This is like assuming you don't type in for things or similar, which is, well, that's also another pretty useful thing to be able to do. You'd probably combine the use of both type inference with the use of semi-efficient handling of dynamic types. So one thing I was aiming for. But yeah, had experimented with things like a dynamically typed time before. Had noted that despite the arguable terribleness of dynamically typed code needing to do a function call for nearly every operation, um, it still worked out only around 3 times slower than a native C version. So it's within the realm of plausible. That's without using any type inference, just straight up using dynamically typed operations. So kind of here, but so technically, like yeah, C, like yeah, Java, C Sharp, and also my own BJX2 language also use this style of array. Although it's a little different in ES2. I can do stuff like yeah. So this creates an array with an explicit size. So if we declare an array this way, it basically produces an array with this type of argument, but it's known to basically be an automatic array. So this notation will not escape whatever bounding scope created it, whereas this one is assumed to potentially outlive the scope that created it. So it's functionally a little different. And this is a different type of array, namely C-style array, which instead of creating the integer array type, this one will just decay into a pointer like in C. So this is C behavior, or Java, or BS2 like behavior, and straight up Java like here. These do sort of exist as language extensions in C mode as well, but albeit with slightly less elegant syntax. Mostly due to needing to deal with the constraints of C. Also, lambdas and all that fun as well. So, extensions for lambdas and for things like dynamic, for things like dynamically bound variables instead of dynamically scoped variables. Another extension. Not all that much stuff that people really need to care about normal C code. My goal is to have a C variant where most existing code works well, as you would expect it to, and not performs terribly. Or performs